Number 2, pitcher throws a ball to a catcher, accelerating the ball from rest. The impulse he exerts on the ball in the process. Third choice there is going to be as large as the impulse the ball exerts on the hand. We saw this in homework number 13 where we had two girls on, I think it's skates, and they push off of each other. They have different masses, but the impulse applied to each person is exactly identical. It's basically an explosion problem. So the momentum before and after have to be the same, total. So one goes one way, one goes the other. So even though the ball goes with a very big velocity to the right, it has a small mass. The person, on the other hand, is going to go backwards with a really tiny velocity because they have such a larger mass compared to the ball. Now these momentums, forward and backward, are identical, meaning that the change in momentum of the person and the ball is the exact same, and change in momentum is impulse. In number 3, you got cars that are coming to a rest, and they're all traveling at the same speed. Passenger is going to come to rest in all 3 cases. One where they're stopped by airbags, one with padded dashboard, and one is just the windshield. So it says in which experience would the person have the greatest impulse? Well, impulse is a change in momentum, m delta v. Person's mass doesn't change. And their change of velocity is final velocity minus initial velocity, which they are all the same. Final velocity is 0, and initial velocity is whatever the cars were driving at in all 3 trials. So they are all the same. Number 4, which car is the greatest force exerted on the passenger? Well, they all have the same impulse, but let's just make up a number. Let's say that impulse is 1,000. That would equal F times T. And when the person is stopped by just the windshield, the time they're going to come to rest is going to be the shortest. You're going to have the smallest amount of time, therefore the biggest amount of force. So whichever one slows the person down immediately, or the most immediately, is going to give the biggest amount of time. Next questions have to deal with this explosion that launches the 3rd stage of the rocket from the capsule. And it says that the mass of the 3rd stage is 4 times that of the capsule. Number 5 asks, during the explosion, the ratio of the force on the space capsule is to the force on the 3rd stage of the rocket is, again, they're going to have the exact same impulse applied to each other. Right? They're moving along, the explosion happens, the impulse is going to be the same forward and backwards. And since those the explosion happened over the same amount of time, whether you're the capsule going forward or the 3rd stage piece going backwards, the time it takes to explode is the same for both, therefore they have to have the same force. Now, that was a really tricky question. That's part of the reason that we took this quiz out of 20 in the gradebook instead of 25, because number 5 was a really tough question. Number 6, the ratio of the change of momentum of the space capsule to the change in momentum of the 3rd stage. Again, if the impulses are the same, the change in momentums are the same. Number 7, the change in the velocities. Now, the velocities can be very different because even though the change in momentum is the same for one piece going forward, one not, their velocities can be very different. Just take a look at what we drew for number 2. You can have very different velocities depending on the mass. So what's the ratio of mass of the masses of these 2 pieces? Well, it's 1 to 4, or 4 to 1. So the slower piece is going to be the heavier one. So if it says here, ratio of the space capsule, which is the lighter piece, it's going to have 4 times the velocity of the heavier 3rd stage of the rocket. So 4 to 1 is your answer. Number 8, after the explosion, the total momentum of the system has to be equal to the total momentum before. We've always mentioned that momentum is conserved. Number 9, 1 kilogram ball strikes a wall with a speed of 10, bounces off at a speed of 8. Magnitude of the impulse is, okay, so impulse is your change in momentum, or m delta v. So that would be equal to 1 kilogram, final velocity negative 8, because it's going backwards from where it was initially going, minus the initial velocity. So negative 8 minus 10 is negative 18. And it just wants the magnitude, so the sign doesn't matter. It's 18. Car A has 3 times the mass but 1/3 the velocity of B. If they collide head-on, the velocity of both cars is going to be 0. If you look at the momentum before and the momentum after, momentum before, you've got car A that has 3 times the mass, so we'll just give it a mass of 3, and 1/3 of the velocity, so let's give it a velocity of 1. And the other car has a mass of 1, because it's got, car A was 3 times its mass, but it has now 3 times the velocity, so you go 3. But they're in the opposite directions, so we'll go with -3 for the velocity. Well, what do you get when you add 3 plus -3? You get 0 for a total, or for a momentum. So that means after the collision they have to have a total momentum of 0 too, which means they're not moving. Number 11, a railroad car is moving along a track at a constant velocity, collides and sticks to an identical railroad car that was at rest. The new velocity that the coupled railroad cars will have will be, so you've got car A going along at a velocity v, collides and sticks to car B that was not moving at all. They're going to stick together and move. So your initial momentum would have been mass of A times velocity of A plus 0 for the momentum of B. And that has to equal to the mass of A and B together, which would be 2m, times some new velocity, we'll just call it Vf. So if you solve for Vf by dividing by 2m, you got m over 2m, which is 1/2 the velocity. Which I realize is on the other screen here, not checked. So I'm going to change. I'm going to change that very quickly here. Number 12, a rubber ball and a lump of clay have equal mass. They are thrown with equal speed against a wall. The ball bounces back with nearly the same speed with which it hit. The clay sticks. Which one experiences the greater change in momentum? So change in momentum is m delta v. So who had the biggest change in velocity is what you're looking at, because they have the same mass, the clay and the rubber ball. So who has the bigger change in velocity? The ball by far, because its velocity goes from being forward to being backward. That's a huge change compared to just going forward and then stopping, which is what the clay does. Right? This is say this was 10 meters per second, and this is 9. That's a change of 19 because it switched directions. This, going from 10 to 0, is just a change of 10. A small car meshes with a large truck in a head-on collision. Which of the following statements concerning the magnitude of the momentum change during the collision is correct? Since it's a collision, and we talked about momentum being conserved, that means the impulse, or the change in momentum, I should say, on each car is going to be the same. So choice E. Small car and the truck experience the same magnitude change of momentum. One is forward, one is backwards. 14, you have to calculate the total momentum of the system. So you've got 8 kilograms going at 5 meters per second to the right, minus 15 kilograms going at 4 meters per second. So that's, I only subtracted because this is 4 to the left, so I could always do plus and then a minus 4. And then you've got 3 kilograms going 2 to the right. So that's going to give us our momentum. So that's 40 minus 60 plus 6. Equals -14. Two ice skaters suddenly push off against each other, starting from stationary position. The 45 kilogram skater achieves a speed of 0.375. What's the speed of the 60 kilogram skater? So, initial and final momentums here. Initially is 0. So finally, you've got 45 kilogram person going at 0.375. The 60 kilogram person is going to have some new velocity, multiply, divide, and it's going to be 0.28 meters per second, the opposite direction, so it would be -0.28 meters per second. 16, we just want the change of momentum of this crate during these 10 seconds, and change of momentum is another word for impulse, and impulse is the area of one of these graphs. So you got a force time graph that looks like this. If you break it up into segments, you can just find the area. So this would be negative 50, this would be negative 25. So your change in momentum or impulse is negative 75 units. 17. Golf club exerts a force of 1,000 newtons on a 0.045 kilogram ball at rest. It's in contact for 1.8 seconds. What's the speed of the ball just as it leaves the tee? So Ft equals m delta v. Force is 1,000 for 1.8 milliseconds, which is 0.0018 seconds. Mass is 0.045. Final velocity we don't know. Initial was 0. Do your algebra to solve for VF, and you get 40. 18, you got a block 34 kilograms and a speed of V. It's behind a block of 81 kilograms and a speed of 0.5. The surface is frictionless, and they collide and stick together. Essentially, we're trying to determine the impulse on the 34 kilogram block due to the collision. A quick way to do this is just to find the impulse on big M and say that it's the exact same as the impulse on little m, because it's just a collision, so they should have the exact same impulses. So the impulse on big M would be m delta v for the big M. And that mass is 81, and its change in velocity, it goes from going at 0.5 meters per second, so 0.5 is your initial velocity, 0.9 is your is your final velocity. Multiply those together, you get 32.4, which is close enough to 32. 19, block of mass 4.4 kilograms moving on frictionless surface with a speed of 9.2 meters per second. Makes a sudden, perfectly elastic collision with a second block of mass m. Second block is originally at rest. After you know the final speeds, what's the mass m of the second block if it moves with a certain speed? So you just elastic collision here. Initial momentum has to equal the final. Beforehand, you got 4.4. It's moving at 9.2. Second block was originally at rest, so m times 0. After the collision, 4.4 kilogram block recoils with a speed of 2.5. So that'd be 2.5 the opposite direction. And the second block, if it moves with a speed of 6.7, that'd be in the forward direction. The m0 cancels out. Do your algebra to solve for m, and you get 7.7 kilograms. 20, during World War I, Germany used this Big Bertha cannon to shoot shells really, really far away. It had a very long barrel. What would be the reason? If you look at the impulse momentum theorem, if you can extend your time frame that a force is acting, you can give the ball the cannonball or whatever it is, the shell, a much larger change in momentum, give it a much bigger velocity from a standstill. So by having the barrel longer, you're exerting this force, this pressure from the gases in the cannon. They're exerting that force for a longer time, allowing the ball or the shell to accelerate for a longer period of time. So that would be choice E.